My screen is visible to everyone, right?
Yes.
Okay. So, with the continuation of our last class, we'll study some more contents as far as this, VLSI system design is concerned. So, today we'll study about CMOS combinational circuit design. So, basically, when we take into consideration, so first one thing that we discussed on the CMOS combinational circuit design is actually static CMOS. Okay, so basically, in these cases, we are taking two main gate and an OR gate for function to learn in terms of land and NOR implementation. Because in many cases, the manufacturing circuit design, sometimes we need also bubble pushing. The bubble pushing, I will tell you also. So, in with the help of that, we can able to make compound gates. The compound gates are actually particularly useful to perform very complex function with relatively low logical efforts. So when a particular input is known to be the test, the gate can be optimized to favor that input. Similarly, when either the rising or falling of edge is known to be more critical, the gate can be optimized to favor that edge. Okay, so it is written here, so you can have a look also here. We have focused here on the building gates with equal rising and falling delays. However, using smaller PMOS transistor can reduce power area and also delay. Now, in this process, what we need to do with the multiple threshold voltage and multiple flavors of gate can be constructed with different speed and leakage power trade-offs. So, so bubble pushing, which I just recently discussed. So, as you know, this is our actually NAND gate, right? So, this is our AND gate. After that, we have NOT operation. Okay. For AND operation, then after that, NOT operation, the inverter operation. Okay. So, this the NAND gate can be also represented in this kind of structure also. Please note that when we have a bubble pushing, that means we put two bubbles here at the input, and this is actually our OR gate. Okay, so this is also can be considered to be a NAND gate also. So this gate that we call it NAND gate, which generally we use. So this gate and this gate are equal. The only difference is that we have incorporated the bubble pushing here. Are you getting my point? So this is actually the bubble pushing concept. Similarly, when we have a NOR operations, okay, so NOR means we have a OR operation and then NOT operation. So this is actually our NOR operation. If you can see here, there is OR gate, and after that we have a NOT operation. So that makes the NOR gate. But if you take into consideration the bubble pushing, so we have AND gate, and before that two bubble pushings, if you can see here. Okay, so this is actually the conventional way of representing the NAND or NOR gate. So both are actually same. So it is way of representation that how you can make it. So this is actually so this NAND gate and this NAND gate is equivalent to each other. This is the NOR gate and this NOR gate is also equivalent to each other. I hope many of you have known about De Morgan's law, right? De Morgan's law tells that if A is one input, B is another input, so A dot B complement is equal to A complement plus B complement. Okay. So this De Morgan's law actually helps the conversion. Okay, so let's say we have a this NAND operation here, and we have to convert into OR operation. So we can make like this. So A dot B complement, that is this is a NAND operation that gives rise to A complement plus B complement. Where plus is our OR operation. In a similar way also, if we have can have a NOR operation, A plus B complement, which is equal to A complement dot B complement here. That means this NOR operation gives rise to AND operation at last. So A complement dot B complement. So this bubble pushing, the way of representation that we call it. So CMOS stages are inherently inverting, and so AND and OR functions must build from the AND, NAND or NOR gates. Okay, and this De Morgan's law actually helps with converting this procedure. Okay, now if you can see here, this is highlighted here in this basis. Okay. So NAND gate is equivalent to an or inverted inputs. Okay, so this NAND gate is a equivalent to an or of inverted inputs, right? So this is we can say as or gate of inverted inputs. Similarly, this figure which we see here, this NOR gate is equivalent to an AND of inverted inputs. Okay, AND of inverted inputs. So please note that this NAND gate or NOR gate. So these are all equivalent here. So either you can represent the NAND gate by this way, or you can represent the NAND gate this way also. The only way of around that we can consider here that this NAND gate is actually or of inverted inputs. Okay, or of inverted inputs. Similarly, this is actually this NOR gate is actually AND of inverted inputs. So, so at the end, we can conclude that so this NAND gate is actually actually conversion. Okay. So the same relationship applies to a gates with more input. The switching between these representation is easy to do with in the when we represent, and this is also called it bubble pushing. Okay. So bubble pushing is very important. So the main thing is that how you can represent any universal gate like NAND gate or NOR gate in terms of its equivalent inverted inputs. So this NAND gate is basically an OR of inverted inputs, and this NOR gate is equivalent to an AND of inverted inputs. Okay. So switching between the representations that we can represent, that we call it bubble pushing. So this way of representing is called bubble pushing. Now let's design a circuit to compute. Let's say it's an example where f is equal to f is the output. Okay, and we have four input. One input is A, another input is B, and another input is C, and another input is D. So four inputs. So if f is equal to AB plus CD, that we have to design with NAND or NOR gate. So how we can do it? So this is the way of representation, how we can make it. So if you can see here, this is one input A, and another input B. So this is actually what? This is our AND operations. Okay, this is our AND operation. Similarly, C and D, this is another input, this is another input. So we get this is another AND gate. Okay. Now the output of this AND gate and another output of this AND gate is connected to the OR gate. Okay. So we'll get the finally the output AB plus CD. Okay. What we did here, we can do in a similar manner by employing NAND and NOR gate here. Okay. So if you can see here, the same output will get here. That means the output to be AB plus CD. But only difference is that we use here NAND and NOR gate. So first we employ here the NAND gate with two inputs A and B. So at the output, whatever we get, so that is given to the NOT gate. Okay. Similarly, another two inputs C and D is given to this NAND gate, and this NAND gate is given to the output of this NAND gate is given to the NOT gate. And whatever the outputs we get from this inverter and this inverter, we give it to the NOR gate. And after NOR gate, we'll give another inverter, and finally we get the output. This output is the same that we got it here. Okay. Similarly, the bubble pushing also, if we can incorporate. So here we use bubble pushing here. You can see here. Okay. So this is the NAND gate. This is another NAND gate, and the output of these two NAND gates. That means here the input is A, B, and here also the input is C and D. So the output is given to the. So this is actually our NAND operation. Okay, NAND operation and NAND operation, and along with we have inverter operation. Finally, we get the AB plus CD. Another way of representation. So we have a NAND gate here with two inputs A, B, and another input C and D. So the output is given to the this NAND operations. So we get AB plus AB. So whether we can get the output by employing this logic circuits, or you can use this logic circuits, or you can these logic circuits, or this logic circuit. So whatever may be, the output remain the same. That means AB plus CD. Okay, you can represent this way, you can represent this way, or this way. Okay, so it depends upon what type of gates you are using. Okay, either you are using simple gate like AND or you are using universal gate like NAND or NOR, or you can employ the bubble pushing, so that we can also incorporate. So in all the cases, we get the same output. So it is the way of representation how we can make the output as per the design design which we require. Okay. So if you can see here by inspection, the circuit consists of two ANDs and OR, as you can see here in this figure. Okay. Now in this figure, if you can see, the ANDs and ORs are converted into basic CMOS series. And in this figure and this figure, that makes in a such way that bubble pushing is used to simplify the logic to three nines. Okay, three nines. Because this is one nine, this is another nine, this is another nine. Okay, so three nines. The three nines constitute the output. Okay. So this is actually the way how we can design or compute any digital circuits. Now, compound gates is a way of representation where we have both simple logic gates and universal logic gates can come together. So that actually our compound gates. So if you can see here, this using this logic, so that this logic actually gives rise to the same output AB plus AD. So this is our AND operation. Then we have a NOR operation, and then we have an inverter operation. So if we can compute this one, we can finally get AB plus CD. Okay. Now, whatever we discussed so far, actually, the static CMOS efficiently handles the compound gates. Uh, Efficiently handles the compound gates, computing various inverting combinations of AND or OR function in a single stage. Now, this function is for example, here we take into consideration of the output AB plus CD can be computed with AND or inverter operation. So this AOI, sometimes we call it AND or invert. Okay, AND or invert. So that is called it AOI. And 22 is given the abbreviation here. So this is shown in this figure. You can see. So the output is actually nothing but the same AB plus CD. Okay. Okay, there is a more way of defining the logic, you can say logic equations. So if you can see here, if you can consider. So here it's a unit inverter. Okay, so unit inverter, if A is the input, so what we will get the output Y complement, right? So this is actually inverter symbol, as you know. And how we can represent it using CMOS. So this is actually our PMOS and this is our NMOS. So they're all are connected in cascade. So this is the input and this is the output. We get the complement. So this is actually inverter circuit that all you know. Okay. So main important thing is that if we have a what you can say compound gates. So how you can implement it using CMOS logic. So that is actually our main idea. Similarly, if you can see another logic equation, that is A dot B plus C complement. Okay. So A dot B plus C complement. Okay. So this is our AND operations, and this is, and whatever the output is there, so that is connected with this NOR gate. So that gives rise to A plus B plus C complement. So this how we can represent using CMOS logic. It's shown here. Okay. So this is actually our two PMOS circuits. These two PMOS circuits are connected in parallel, and that is connected in series. And what up and the overall the A B C that we see here, because this is a three input circuit. So that is connected to the this NMOS circuit here. So this is NMOS, two NMOS are connected in series, and then these two NMOS A, B input is connected in parallel with C. Okay, and finally we get the output like this. Okay. So if in the question it is asked that implement these compound gates using uh, CMOS logic, so you have to draw like this. Okay. Similarly, another way of representation, let's say we have another example, A dot B plus C plus D. Okay, complement. So here if you can see here, we have a A, B, two inputs that is connected to this input of this AND gate. Another again another input C and D that is connected to the input of this AND gate, and the output of this AND gate of input A and B, and the output of this gate of input C and D is connected to the NOR gate. So finally, we'll get this uh, equations. And how to represent in the CMOS diagram. So this is the way. Okay. So this is the way we can represent. So if you can see here, so this A and B are connected. A and B PMOS are connected in parallel, and then C and D also connected in parallel. And then here A, B, A and C are connected. The NMOS circuit is connected in parallel. B and D connected in parallel, and the overall output is given as here. So this output is nothing but Y is actually A dot B plus C plus D complement. Okay. Similarly, another let's say compound gates. Let's say we have to design. So let's say A dot B plus C plus D plus C complement. So how we can design? So this is actually A, B, C, D, and E. Okay, five inputs are there. So first B and C. So this is OR operation. So this is a B plus C. This is OR operation. So we give one gate. Then whatever the output of OR gate is given to the along with the input A, we give it to the AND gate. And again, D and E input is given to the this AND gate, and the output of this AND gate is and output of this AND gate is given to the it serves as the input of this NOR gate. Finally, we got this A dot B plus C plus D plus E complement. So this is actually realization of this compound gate. This realization of this compound gate can be implemented using CMOS diagram. You can see here, this is the way how we can represent this logic equation. So this is our PMOS is connected in parallel. Another this PMOS is connected in series B and C. A is connected in parallel with B and C. Again, D and E are parallel to each other. Similarly, this A, E and D are connected in series. A is in parallel with each other, and this is connected in parallel with NMOS B and C. And finally, we get the output Y as 8 of B plus C plus D plus complement. Okay. So you please practice whenever you're in the free time. You please practice such kind of examples. That means how to design and implement these compound gates using CMOS logic. Okay. So that you have to do it like this. So there are three examples I have shown here. First example, as you know, this is normal CMOS inverter that you know, but this one is important because how you can design any logical equation using this CMOS logic. Okay, so first one is the our logical equation. Second one is the our gate representation in the gate, and third one is the implementation using CMOS logic. Okay. And this one is what we see. This is AOI, which you see here is AND or inverter. Okay, so this is that we call it AOI, and this 21, 22 is given as the abbreviation. So in general, the logical effort of compound gates can be different from different inputs. Okay. So as you can see here in this figure, the how the logical effort can be estimated using this AND or inverter operation. Okay. And more complex compound that you can say AND or inverter gate. Now the transistor bits are chosen in a such a way to give drive as a unit inverter. Now, the logical effort of each input is the ratio of the input capacitance of that input to the input capacitance of the input of the inverter. You can see here the AOI, that means and or inverter 21 gate. This means the logical effort is slightly lower for the OR terminal C than for two NAND and terminals A and B. Okay. Now, this parasitic delay is estimated from the total diffusion capacitance on the output node by summarizing the sizes of the transistor attached to the output. So, overall, uh, uh, it's very important that if you have a given compound gates, okay, so because this chapter is all about the design of compound gates, okay. So, if you have a compound gates, how you can design it using CMOS logic operations and with the illustration with the corresponding uh, uh, logic gates. So that is important. Okay. So whenever the question will ask to design these compound gates, so you have to draw these compound gates and design it with this CMOS logic. Okay. So that should be your way of representing. Okay. So any doubts so far, which I have taught in the class? Any doubts? Any doubts so far? Okay then. Uh, okay, one digital assignment I have uploaded in the Moodle. So all of you please, because today is the last date to submit. So all of you please submit the digital assignment by today. Okay. So please submit by today. So today is the last day. Okay. And so we'll meet at 3 p.m. today in the online class. Okay. The online class link I will share with all of you prior to that. Okay.